practice problem for you guys that I realized I did not do a good job of getting you an example video before. So let's go ahead and do it. It's number 8, and it is a man skis down a slope 200 meters high. What is his velocity at the bottom if no energy is lost? And if his velocity at the bottom of the slope is 20 meters per second, what percentage of his initial gravitational potential energy was dissipated due to friction and air resistance? Well, let's just jump in here and we'll talk about how we can do this. So first of all, let's get a picture. Here's the ski hill, and it's 200 meters high. Okay, let's not deal with the energy loss. Let's just find the velocity if no energy is lost. So we know not a lot, right? We don't know the man's mass. We'll give him a couple of skis here. He's going to ski down the hill, and we want to know his velocity. What I do know is this. Based on our energy pi descriptions, at the top, his E grav is m times g times h. And if everything goes well, at the bottom, he's all E kinetic, which is 1/2 times m times v squared. Which means all of this energy should turn into all of that energy. And so therefore, if E grav at the top equals E kinetic at the bottom, then the mass times the gravity times the height should equal 1/2 times mass times velocity squared. Since it's the same man, the mass is the same, therefore these masses cancel. And I know gravity, because that is consistent. I know the height. What I don't know is the velocity. So if I do a little algebra magic here, I'm going to get 2gh equals v squared. A little flip-flop and a square root, and I get v equals the square root of 2 times g times h. And we can go ahead and substitute in the square root of 2 times 9.81 meters per second squared times the height of 200 meters. Okay, let's go ahead and do that. Square root of 2 times 9.81 times 200 is equal to, 62.6. That seems really fast. Give me a second just to double check that here. Let's go 2 times 9.81 times 200. Although 200 meters is a really, really, really steep hill. All right, we'll take the square root of that just to double check. Okay, and then this would be meters squared over second squared. Take the square root of that. That's meters per second. So, in the first part of that problem, the trick here is to be really good at understanding energy pies, where the energy comes from, where the energy goes to. You can set them equal, and then you can cancel out the factors. As far as the second part of it, what percentage of his initial gravitational potential energy was dissipated due to friction and air resistance? Well, so if you know that he's going 20, you got to be a little careful with this. 20 meters per second. You could find his energy, right? His kinetic energy would be equal to 1/2 times mass times the velocity squared. Or we could work backwards now if we want to. Using the velocity, we could work backwards and solve for his mass and then plug it into this. But what I would do is I would just take 1/2 time. Oh, shoot. Sorry, we can't use mass there. So if he's going 20 meters per second, we just need to figure out what percentage that is. So 1/2 mass times velocity squared over 1/2 mass times velocity squared. It would be, well, these are basically going to go away, right? It's the ratio of his 20 meters per second squared to his 62.6 meters per second squared. Whatever percentage that is, that's the energy that you kept, and the rest of it would be dissipated. I like to keep these videos short, so I'm just going to stop there.